Hello everyone, my name is Vito Kortbeek and welcome to my talk about WARio, efficient code generation for intermittent computing. I did this work together with my collaborators Shrudip Ghosh, Josiah Hester, Simone Campanoni, and Premiswa Pawelczak. Before I actually start the presentation, I want to take a small moment to remember Elko Visser. He was a PL professor at my university and he passed away unexpectedly last year. So efficient code generation for intermittent computing. And especially the intermittent computing, I'm assuming that a lot of you don't necessarily know what that means exactly. So let me just build up to that first. So it applies to small embedded devices, such as IoT devices. And we're expected to have many, many IoT devices in the coming years. Some expectations, for example, this one expect over 20 billion of them just by 2025. And that's his only connected IoT devices. So there are also people talking about stuff like smart dust, where there are just thousands of devices just spread out through the city in walls, whatever, monitoring everything. And this is all very cool, of course, but there's a big problem there. Like, how are you going to power all of these devices? Because they might not be next to an outlet. So obvious choice is batteries, but batteries are not really perfect for this. So one thing you can imagine, if you have billions and billions of devices, you'll also have billions of batteries that will eventually run out and or have to be replaced. Look at your phone, like you have to replace the battery before anything else. And this is just an ecological problem on its own. So landfills will be basically swamped by just batteries at that point. But that's not necessarily even the biggest problem, or maybe not a problem you actually care about. A big problem is also just that it's very annoying to actually replace the batteries. So imagine if you have billions of devices, hundreds of thousands, whatever, and they might run out of energy maybe what, like every couple years? That's still a lot of batteries you have to change every time. And some poor soul has to go around and actually change them, which will be terrible. And some of these devices are proposed to be built into walls, roads, or anything. And you cannot just open up your wall to just change the battery. That's going to be very inconvenient. So we want something else. So what could that something else be? Other energy sources? Well, a very expected one is probably energy harvesting. So where you get energy from the environment. A big, like well-known example of that is of course little solar panels, but it can also be anything else. It can be vibration, thermal differences, radio waves, whatever. But there's a problem with that. So we're targeting very low power microcontrollers at this point. So not Raspberry Pis or phones, really low power microcontrollers with some sensors on there. But even then, the energy you can get from, for example, radio wave harvesting or temperature differences is not enough to actually continuously power these devices. And even sometimes when it's definitely not reliable. They turn on and off very frequently, or the power is available, the energy is not. So the problem that occurs then is that the execution of the processor essentially happens in short bursts. And these bursts can range from maybe 50 milliseconds of execution up to a second of execution. But in general, they're very small, too small to essentially finish your whole program for a lot of cases. So this is where intermittent computing comes in. So this is maintaining forward progress while executing amidst these power failures. So below here you see an example graph where you can see the energy is essentially harvested. In this case, it is harvested in a very small capacitor, but still that only gives us milliseconds of runtime. And then once we turn on, we decide to execute some code and then it dies again. So the processor completely turns off. We collect some more energy, we do the same, rinse and repeat. But the problem is if we start the program all over again every time, we will just never finish. So we need to save where we're at and continue in the next on period, essentially. So then the problem becomes, okay, cool. How do we actually save this state? So in a normal embedded system, you'll have some SRAM that holds your memory and you'll have your registers. Okay, so we can copy all of that into a non-volatile media. Okay, that's fun, but copying all the memory every time, that can be quite cumbersome as well. It can take a long time, so it might not be an ideal solution. An alternative is using non-volatile main memory. So the main memory itself is non-volatile and not in stuff like flash, for example. It's in things like MRAM. So it's just a different form of memory, which is non-volatile. So it will just persist across these power failures. And at that point, it gets a lot better because we only have to copy the registers to save the state and restore them when we boot back up. Now, For this, there are two main strategies. You have just-in-time checkpoints and you have statically placed checkpoints. And a checkpoint is essentially saving the state. So just-in-time checkpoints are cool because you can push them really to the end of the program where you can just save just before the power fails, you'll save your registers and you restore them next time. Now, this might sound very cool, but it also comes with some problems, namely that you have to predict when the system is actually failing. And again, the energy harvested sources can be very erratic, and predicting how much energy is actually used, especially when sensors get involved and at very low voltages as well, it's not that easy to actually track when you have to actually save the state. And if you're wrong, you're kind of screwed, which will slow later on, because then you might be inconsistent from the memory you're actually expecting to be. So this is a problem. So the other way of doing it is statically placed checkpoints. And here the compiler tries to place the checkpoints in such a way that it is impossible to essentially corrupt your memory state. So whatever happens, you can restore a valid state of the system without having to totally reboot and redo the system from scratch. And this is also what we're going to focus on. But to illustrate a bit where those checkpoints actually have to be placed, we have to talk a little bit about the write after read problem. So this is with regard to the memory. So if a power failure happens after a write after read the memory, restoring the last checkpoint can lead to an invalid read during the re-execution. So what do I mean by that? If you see this little code snippet of pseudo assembly, you can see your non-volatile memory holding a variable a, and it's now 0. Next, we read it into a register. We add some number to it. Now it should be 42, and we write it back. So the non-volatile memory is 42. Okay, that's all great. Now the power fails, and we restore it again from the checkpoint. Now we read A. Now we read 42 instead of 0. We add 42 to it again. Now it's 84. So you can see for this small example, you can see if this is some pointer manipulation, some control flow dictating stuff, you'll just completely mess up your program. So this is a problem. Now, how do you solve that? You solve that by putting a checkpoint between the read and the write of this write after read to non-volatile memory. So if we do go through these steps again, we can see that, okay, it's read, it's added, and power fails. But now we restore from a later point. So we just only write our contents of register 1 again to the non-volatile memory. So we have the expected output of 42. And here, the reason we can still restore the register is because the register is actually part of our checkpoint content. So in this case, the checkpoint only consists of the registers. Now this is great, and this is the related work. But the problem is, you might imagine that it happens a lot in a program. There will be a lot of write after read, and even though the checkpoint then is very small because it only contains the registers, there will be so many of them, this still kind of creates a problem in terms of overhead. Now we come to what we actually did, our work. So our work is a set of compiler transformations that reduce the number of required checkpoints, but we still want to essentially be safe. So still, whenever happens, we can still restore from a correct point. So we want to reduce them, but we want to still break all of the write after read dependencies. Now, we do that by a number of ways. The two ways I will discuss in the presentation here are clustering war writes and clustering war writes in loops. But we also do other stuff like protecting stack pointer modification, WARio inlining, and utilizing a hitting set checkpoint placement algorithm also in the backend in addition to the middle end. But for these, I would like to refer you to the paper. So why would we even want to cluster the war writes? Well, if we take our snippet again from before, but we now have two iterations of it. So we first read A, and then we read B, and we write them away. It's all cool. But if we place checkpoints now, we'll see they have two checkpoints. All right, so far so good. Now, if we move the first write down a bit, so past the read of B, because they are not affecting each other, we can do this. And if we now place a checkpoint, suddenly we can break both the write after read dependencies with just one checkpoint instead of two. So we halve the number of checkpoints, which is good. Now, how do we do that? So WARio uses the Noel framework, which is an extension to LLVM, which makes it easier to analyze the programs. It gives us better alias analysis information, some other memory dependency information, and it also makes it easier to transform loops, for example, which we'll use heavily. And then for each write after read, WARio checks if it can safely move the write past the read of another write after read if they're not dependent on each other. Now, where this is very effective is in loops. So normal programs, but embedded systems programs especially, loops happen a lot. Now, you don't have to actually read all this. Please don't try to read it. This is just to illustrate you through the process what we do. But there will be often will be a very hot loop that will execute something similar to what's on the bottom left, which is our example we've been using before. So it will read something, it will modify it, will store it again, and it will have a write after read. So now every loop iteration will have a checkpoint. And this can go out of control. And what we've seen with a lot of applications is this is where a large part of the overhead comes from, even though it's just a couple of instructions. So we don't need that many checkpoints over here. Now, that's over here. Now what we do is, okay, we want to cluster our writes from the vars also in loops. Now, how do we do that? We first unroll them. So we have multiple iterations here. And then we do something similar that we discussed before. So we try to cluster the stores or the writes actually together so we can use less checkpoints. But now we have a bit of a problem because if our loop, instead of iterating 3 times, only iterates 2 times, we never write our memory, which is a no-no. So we need to modify also our early exit. So whenever the loop exits, it still needs to write away whatever it had at that point. So we cannot just not do it. Okay, so far so good. Now, because these loops are they have a big effect on the actual program, we want to be a little bit more aggressive than we are with the normal case of the write after read clustering. So even if they have some dependencies and we can easily check them, and even at runtime, we might add some dynamic checks in the loop to check whether we can just still move them even though they have some dependencies. Normally adding dynamic checks in a loop might be a very bad idea, but in this case, because the register checkpoint, even though it's only the registers that are checkpointed, it still has some overhead of managing how to do that. It's still beneficial to do it like this. And now if we place a checkpoint, we can see that we only need 1 for the 3 iterations that we unrolled. So instead of 3 checkpoints for 3 iterations, we only need 1, and we can scale this up, obviously, to reduce the amount of checkpoints in loops. So this is the evaluation of that. If you look at the top part of the graph, you can see that depending on the amount of time we unroll it, will go down, but eventually it will level out because we also add instructions and the effect will just lessen, essentially. And then a good number to pick here is 8, which we used for the rest of our evaluations as well. So these are some bars for some benchmarks. This also includes a lot of bars for the other optimizations we talked about, which we didn't talk about, which are in the paper. But everything here is normalized to uninstrumented C. The thing is with uninstrumented C, it will never work on the intermittent device, but this will be the case if you just run it without checkpoints, just let's go. And then from the bars on the total left is our related work. Then the one to the right is our related work, but with better alias analysis information. And the total bar on the right is essentially the combination of all our transformations in our work. If we look at some benchmarks, for example, SHA here, you can see that a big part of the improvement actually comes by just improving the alias analysis which was used so we can find better write after read dependencies. Because we, of course, have to be conservative because even if it can cause a write after read, we put a checkpoint because we don't want to just take a chance over there. And there is also other benchmarks that first we can reduce the amount of checkpoints a lot by adding that better alias analysis, but also then our other optimizations really cut it down by more even. And there are some benchmarks that just, it didn't really do anything. Sometimes because there were already very little overhead such as this, but also sometimes if none of our optimizations, of course, affected, then it won't improve. Now, that was essentially it. So we built WARio, a set of compiler optimizations for battery-free systems with non-volatile main memory. Everything I talked about here is open source. You can find it on GitHub. You can scan the QR code and you'll go straight there. We also have Artifact available, which is also reusable. So you can even play around with it and put your own code examples in and see where checkpoints are placed or how much efficient it would be. And lastly, some self-promotion real quick. I am open for job opportunities from 2023. So if you have something in the embedded space and you think I would be suited for it, just come talk to me somewhere during lunch or whenever I'm walking around, or just send me an email. Thank you.
Thanks. Cool talk. Seems like a fun space I've never thought of before. Most of the optimizations that you showed here dealt with pushing writes and reads through straight line code. But for example, in a loop example, you might be able to do better by separating out into multiple loops than by loop unrolling. Have you considered pushing optimizations through control flow constructs?
You could, but it becomes very dangerous real quick with making sure the semantics of the program are still correct. So I think that could be something to look into, but it can be very difficult. And what we've seen is that the most performance we really get from loops, just because they're just very small pieces of code that are repeated a lot. And in that case, we don't need checkpoints that often. So that's why loops are very like good thing to target in this case. But thanks for the question.
Yeah, it's cool work. So here your checkpoints are statically placed based on like the memory dependencies. So do your benchmarks handle peripherals? Because sometimes peripherals can be very sensitive
Yeah.
to exactly where the checkpoints
Yeah, that's a
occur.
very good question. So peripherals for this, we kind of acknowledge that they exist, but we say it's kind of different, like it needs different work to approach it. So there are peripherals supports in other works and you could apply it to this, but we don't directly focus on them here. But yeah, that's a very important point that has to be tackled as well.
Hi, I was just curious, is there any possibility of moving the checkpoints for an efficiency purpose, but maybe they get moved back far enough that I don't have enough power to actually make it, and I accidentally get caught in a aliveness problem where I'm not
Yeah.
proceeding to checkpoints?
That's actually a very good question. So the reason we didn't tackle this for this is that we didn't experience it for the real life traces we had. So we never ran long enough basically without a write F3 where I just had to put a checkpoint. But that's definitely something we also noted in the paper that needs some exploration. Like what if there are programs that just never generate write F3s? You'll have to put those checkpoints in yourself. And you can, in theory, you could even do that by using a timer because in theory you can put checkpoints wherever you want. So yeah, that would be some way to resolve that. But that's a good point.
With the timescales that you had on your diagram very early on, it sounded like you had power for like tens of milliseconds, and then you lost powers for tens of milliseconds, and so at those timescales, what would go wrong if you just added a capacitor to just bridge those gaps?
Yeah. So a capacitor. So a couple things, of course. So first off, if your power source is not generating that much energy, your capacitor might just leak it away itself as first. So that's a problem. Of course, size is also a problem. And if you do want to eventually sense things, which is the ultimate goal, of course, you might not want to wait like such a long time to turn on and then just have a long time to sense because that sometimes doesn't make sense. You want to just turn on, sense a little bit, turn off, and then do your processing in between. So it's also when you want to essentially be alive.
Cool, thanks.
But for some applications, it would definitely be okay to just put a bigger capacitor on there.
Sweet, thank you very much.
Thanks.